Let's move on and talk about now the Gaussian mechanism. This is like the classic algorithm in epsilon delta or approximate differential privacy. But before we get to that, let's talk about the L2 sensitivity of a statistic. This is very similar to what we've looked at before. The L1 sensitivity, you might be able to guess what the difference is, but let's go through the motions anyways. So let f be a function which takes in some data set of size n on some domain and outputs something which is a real vector of dimension k. Then the L2 sensitivity is the following quantity. It's going to be delta sub 2 and f, which is equal to the max over x and x prime, which are, as usual, neighboring data sets. And we just take the L2 difference between the L2 distance between their values. So this is the L2 sensitivity. It shouldn't be any surprise to you. The sort of only difference, recall last time we considered the L1 sensitivity, which is the L1 distance between the two values and the max of that. But here we're going to consider the L2 sensitivity because it's what sort of works nicely with the Gaussian mechanism. So what is the relationship between the L2 norm of something and the L1 norm? Let's suppose let's just talk about that real quick. Suppose we have that x in r to the k, then we have the following relationship here. We have that the L2 norm of x is less than or equal to the L1 norm of x, and this is less than or equal to a square root k factor times the L2 norm of x. So what this is saying is that the L2 norm and the L1 norm are within a square root of the dimension factor from each other, and therefore the L2 and L1 sensitivity will be within a square root k factor of each other as well. So this will actually make a difference at some points, as we'll see in an example in a little bit, where doing an algorithm that uses the L2 sensitivity rather than the L1 sensitivity will allow us to get a much smaller error, something that's smaller by a factor of square root of the dimension. Okay, but so that's the definition of L2 sensitivity, just saying how much the output of the function can change in L2 norm. Now let's see, another tool we'll need is the Gaussian distribution. I'm sure many of you have seen this, but let's just write it just so that we're all on the same page. So it's a distribution parameterized by two things. So it's going to have, this is the univariate distribution, the univariate Gaussian. So this has mean mu and variance equal to sigma squared. And it has the following density function. Once you see this enough, it looks kind of intimidating, but you kind of get used to it and can remember it. Yeah, so that is the density of the Gaussian with mean mu and variance sigma squared. So what can we say about this? What do we want to say? Well, the first thing you want to note is that let's compare this briefly to the Laplace distribution, which is something like 2b x buff minus absolute value of x over b. You can see that this one has lighter tails than, the Gaussian has lighter tails than the Laplace distribution, meaning that as you go further out and further away from the mean, then this will be smaller than this will be. But yeah, you can see that they both sort of decay exponentially at least. So they're kind of similar, but they're also kind of different. So we can see some visualizations of what Gaussians look like right here. These are Gaussians. You can see this like skinnier one is one with a smaller variance. This is the standard normal Gaussian. This red one here. Here's a wider one with a higher variance, and here's one with a different mean. So yeah, this is kind of just some pictures of Gaussians and what it should look like. I'm sure many of you've seen this before. Informally, say like a bell curve is another term. Okay, so that's the Gaussian, which I hope should be familiar to many of you. with this and with the sort of two notions we have here, we have the Gaussian distribution and we have the L2 sensitivity. With that in place, we're ready to talk about what the Gaussian mechanism actually is. And, if you've been paying attention, you'll probably guess that based on the name Laplace Mechanism, which adds Laplace noise, well, here instead we're going to add Gaussian noise. So here is the definition of the Gaussian mechanism is as follows. So we're going to let f be some function, as usual, from x to the n, some domain, takes in n data points, and maps to r to the k. Then the Gaussian mechanism is the following algorithm. It takes the function on the data set, and it adds, Gaussian noise to each coordinate. And how much Gaussian noise does it add? Well, it'll add these as independent Gaussian noise, where each one is distributed as the following. I'll write it. It might look a little bit intimidating, but then we'll parse it a little bit. Okay, so this is Gaussian noise, but let's simplify this a bit. This is the Gaussian mechanism, and the claim is that this is it's epsilon delta differentially private. We'll get into this in a little bit, but we'll prove this a bit later. But the main important thing that you should note here is how big is the noise here? How big is yi going to be? Well, what we have here is the variance. The variance, I'll write this a little bit simpler, but it's like the L2 sensitivity squared over epsilon squared times log 1 over delta. Let's say I'm going to get rid of some of these constants. So this is the variance, and this gives us a standard deviation equal to the L2 sensitivity divided by epsilon times square root log 1 over delta. Let's recall the Laplace mechanism. If we wanted to do the Laplace mechanism, then this would have the sensitivity equal to the L1, the sigma, the sort of amount of noise we would add to each coordinate would be the L1 sensitivity divided by epsilon. So you can see kind of the difference in the scale of the noise that we add via the Gaussian mechanism and the Laplace mechanism. The Gaussian mechanism will have the square root log 1 over delta, which we kind of don't care so much about. But really, it's kind of the same in the sense it's the sensitivity divided by epsilon. The main difference is the fact that Gaussian noise has to be based on the L2 sensitivity, whereas Laplace noise is going to be based on the L1 sensitivity. And in fact, like we mentioned, these can be off by, say, up to a square root of the dimension factor. So in fact, the idea is that, as we'll see in an example in a sec, we will have potentially worse error if we want to add Laplace noise versus Gaussian noise. Of course, this comes with a benefit in the sense that Laplace noise gives you a stronger privacy guarantee of pure differential privacy as opposed to approximate differential privacy. So it's kind of a trade-off. Do you want less error but a weaker privacy guarantee, or more error but a weaker sorry, I got a bit confused there. The obvious correspondence. Laplace mechanism is a stronger privacy guarantee, but adds more noise, whereas a Gaussian mechanism is a weaker privacy guarantee, but adds less noise. So there's sort of a trade-off there, a choice between which notion is appropriate for you. And let's actually go over this with an example to see, what I'm talking about. So let's suppose we have a very simple setting where we want to estimate, the mean of a data set. We've done this many times before, so like I'll write it here sort of suggestively, and then I'll show you how it's different. So we've seen this many times before, where each xi is in 0, 1 to the n. Sorry, each x, let's just say the whole data set, x is in 0, 1 to the n. So this is what we've seen before, where it's sort of like a vector of bits. But now what we're going to do is to change it up a bit and get some interesting behavior going on. we're going to look at the case where each coordinate, let's put a d in fact for dimension, each data point is going to now be a vector of binary values. So you can imagine this is like a bunch of survey questions. Each person tells you their answers for each survey question, and you want to find out the sort of answer to all of them simultaneously. Yeah, so the goal is here to find some sort of estimate of the average result in L2 norm. Okay, so let's analyze, two different ways of privatizing this. So first of all, what is the sensitivity of this function? Well, let's take a look at how much, what's the sensitivity? Imagine, we take say x1, and we make it go from is equal to the all ones vector, and then it goes to x1 is equal to the all zeros vector. So how much does this affect the statistic? Well, the sort of difference that this incurs is equal to, the difference between the neighboring data sets here would be, since all the other terms cancel, it would be sort of the L, it would be the norm. Okay, let me write this first. It would be, this is the sensitivity, essentially the norm of this vector, which is equal to just 1 over n times 1, where the norm here is either going to be an L1 norm or L2 norm. So what is the L1 norm of this? Well, this is equal to just summing 1 over n over all the coordinates is equal to, say, d over n. And on the other hand, what is the L2 norm of this vector? The L2 norm is equal to, if you do the calculation, it's going to be, say, so summing 1 squared for all of them and then taking the square root. So this will be, in the end, if you do the calculation, I claim that it's going to be square root of d divided by n. So I promised you, remember before where we talked about L1 and L2 norms, I claimed that they can be off by a factor of the square root of the dimension, and it seems for this very simple statistic where we just average a bunch of binary vectors, we actually do realize this type of difference in the sensitivity, where one is the L1 sensitivity d over n, whereas the L2 sensitivity is a square root d over n. So let's see, like, if we wanted to do the Laplace mechanism, what we would do is we would take f of x plus, Laplace noise of magnitude d over epsilon n, and this is sort of raised to the power of, like, tensor, to the d. This is just me saying that this is a shorthand notation for saying you add this independent noise to each coordinate, and then, the error is going to be essentially equal to how big this noise is. Like, how much noise did you introduce? The overall, like, the error you introduce in L2 norm is the, like, L2 norm of this, say, Laplace d over epsilon n to the tensor d. And the claim is that this is going to be roughly equal to, in L2 norm, this is going to be equal to, roughly d to the 3/2 over epsilon n. That's my claim. You can check this for yourself, but why is that? The reason is because you have a bunch of random variables, y1 through yd, and the claim is if you're adding noise which is approximately of magnitude d over epsilon n to each coordinate, then doing the, like, norm calculation for how big the error will be overall, it'll essentially multiply it by a factor of square root d when you consider the L2 norm. Yeah. So that's what the error would be if you use the Laplace mechanism for this case. How about the Gaussian mechanism? Well, like I said, this time you have to add, say, less noise. It's just f of x plus, let me write it as, Gaussian 0, and then the standard deviation is going to be, I'm going to leave out some of these log 1 over deltas, but the standard deviation is going to be square root d over epsilon n. Then you square it for the variance times the, let me just use this tensor product to the d. And the claim here is in a similar way that we had, noise of magnitude d over epsilon n in each coordinate, and that makes us have an overall noise magnitude of d to the 3/2 over epsilon n. Well, in this case, the overall error for the Gaussian mechanism will be something like the magnitude of this Gaussian noise here in L2 norm, which is going to be roughly equal to d to the epsilon n, or d over epsilon n. And again, this is just basically taking the coordinate-wise standard deviation and multiplying it by square root d, which will give us the L2 error. And you can check this yourself, that this is roughly what it'll be. So these were a lot of calculations, but let's see what we actually concluded here. We can see that for the same problem, trying to privatize the average of a bunch of bit vectors, if we wanted to use the Laplace mechanism, we would introduce L2 error of magnitude roughly d to the 3/2 over epsilon n. This will give us a strong guarantee of pure differential privacy. On the other hand, if we wanted to do approximate differential privacy, then we'd have a weaker privacy guarantee, but you can see that we have less L2 error, which is approximately d over epsilon n. So you have to choose which case, which one you really need. Well, how strong a privacy guarantee, and if you're okay with a weaker privacy guarantee, especially in higher dimensional settings, it could be better to use the Gaussian mechanism. Okay, so that's a neat example showing sort of the different utilities of the Laplace versus the Gaussian mechanism and how things might differ in terms of the accuracy you can get. Now, the next and sort of main thing that we're going to prove in today's lecture is going to be privacy of the Gaussian mechanism. So, and again, let me just write this one more time. What exactly is the Gaussian mechanism? The Gaussian mechanism is the following. M on x is equal to f on x, and then you add some Gaussian noise. Let me write it in sort of a more compact form, which I'll explain in a sec. We write it as the standard deviation times the identity. So this will be I'm leaving out some of these constants just because if you want to check them carefully, then that's a lot more work. But yeah, this is kind of how it would work. So we're going to add noise to each coordinate of magnitude delta over epsilon times square root log 1 over delta. That's the Gaussian mechanism. Like I said, we're going to ignore these constants because if you want to prove it carefully, then maybe look at the book. But we're going to be a bit loose with these constants here, just for the sake of teaching it. Otherwise, it'd be a bit more technical than I'd like. Okay, so before we continue further, I'm just going to remind you of some basic facts of Gaussians, which we're going to use. And these are going to be facts involving the fact that essentially saying that Gaussians are linear in terms of their variance. So let's suppose we have, maybe that's not the right variable. Let's say y, which is distributed according to n, 0, 1. Then we have that if a is a constant, then we have a times y is distributed as n, 0, a squared. So you can see that, if you multiply it by a number, that sort of multiplies its variance by the square of it. And similarly, you can add two Gaussians, like, if you also have that z is distributed as n, 0, 1, then, what do I want to say? The variances essentially add. So let's just do this in generality, like a AY plus BZ. This will be distributed as Gaussian with mean 0 and variance A squared plus B squared. Essentially taking the two variance components of the components and adding them together to create one variance. Okay, so this will be a useful fact, but yeah, that's a bit of a diversion. We're going to focus on the Gaussian mechanism privacy proof, essentially saying that let's consider the privacy loss random variable of this algorithm, and then see if we can prove that it's going to be bounded above by epsilon with probability 1 minus delta. Recall that this is all we need because we're just trying to prove that it's epsilon delta dp, which is exactly what this is. So what's the strategy we're going to use here? Well, the first thing we're going to do is we're going to do the following. We're going to, step 1, say that the privacy loss random variable is actually pretty nice here. Like we saw for when we looked at the Laplace mechanism, it was kind of weird, right? You had this weird point mass and something odd going on between it. But for the Gaussian mechanism, it's actually going to have quite a nice privacy loss random variable. The privacy loss random variable is in particular going to be a Gaussian with kind of weird parameters, but we'll get to that. The point is that step 1 will be to show that this random variable is going to be a Gaussian, and then once we know it's a Gaussian, all we have to do is use standard Gaussian tail bounds in order to prove that it's going to be bounded by epsilon with probability 1 minus delta. Okay, so the main theorem, or the main lemma that's going to be doing most of the lifting is the following perhaps intimidating looking lemma, but it says that let x and x prime be neighboring data sets, and m of y is the Gaussian mechanism, except we're just going to leave the variance sort of unspecified for now. It's just going to be some sigma squared. So we run the Gaussian mechanism. Then the privacy loss random variable between m and m on x and m on x prime is going to be distributed as this. So what is this? This says it's a Gaussian with this mean and this variance. So the mean is going to be the sort of difference in L2 norm between the two functions on those two data sets squared, divided by 2 sigma squared, and the variance is going to be the same thing actually up to a factor of 2. So this might be a bit weird, but it's essentially saying that we're going to set it to be we're going to show that the privacy loss random variable is a Gaussian. Okay, so how are we going to prove this? We'll do this as follows. So without loss of generality, just sort of as a shorthand for f of x minus f of x prime, we're going to let this be equal to some vector v. So that's kind of the difference, and it's going to be the thing that shows up in the numerator here squared. So that's the shorthand for the difference, and we're going to assume that our noise, our random noise, is going to be a vector like lowercase x, which is distributed as n0 sigma squared times I. So that's exactly what the Gaussian mechanism does. So what is a privacy loss random variable? Well, let's just write it out explicitly. So it's going to be the following. It's going to be this goes up in the numerator is kind of like what the real realization is, and since it's the Gaussian, you just look at the value on the data set plus the noise. That's literally what we compute here, and then we compute the probability on the other data set at the exact same point. So now what is this value here? Well, let's just sub it directly into the PDF of a Gaussian, because these are just Gaussian distributions. Mx is a Gaussian, and m on x prime is going to be a Gaussian. So this can be written as the following ratio of densities. Okay, now where did this come from? This is just basically saying, you know, looking back at the density of what the Gaussian is in the multivariate setting especially. All we're saying is that, you know, this is a Gaussian, this is going to be distributed as a Gaussian with mean f of x. So the probability of seeing something which is f of x plus the noise vector x is going to be, you know, the value of this realization minus the mean. So that's why we subtracted out this f of x. And that's sort of how far it is from the mean of the distribution, and the PDF is there. Similarly, for the bottom thing, this is going to have, you know, this is going to have mean equal to f on x prime. So, you know, what we have here is the distance from the sort of L2 norm that we have to put into the PDF is going to be x plus f of x minus f of x prime. And since we use this, it's just going to be x plus v. So this is the ratio of the two densities. And you might be wondering, there was this 1 over square root 2 pi sigma squared. Well, that went away just because of, you know, it's in the numerator and the denominator, so they both go away. They cancel each other out. Okay, we're going to use the rules of exponents and this logarithm. And if we do both of those together, like sort of taking this into the numerator and combining it in the same exp, but then canceling out that x with this natural log, we're going to end up with the following expression here. So this is just combining these, taking the log. And now what we can do is expand these L2 norms into their components. So recall that the L2 norm of a vector can just be written as follows. J squared. This is the first thing. And then minus, this will be xj plus vj squared. So this whole thing is sort of in parentheses. Okay, so this is just expanding out what the definition of the L2 norm is, and since it's squared especially. And this can be written as just kind of, what we're going to do is we're going to expand out this square. So what we're going to get is the fact that this becomes an xj squared, and this cancels out this xj squared. And then we're going to be left with this vj squared and 2xj vj. So essentially 2xj vj plus vj squared is what's going to be left. And a negative sign will cancel out there. So convince yourself that the sort of simplification of this will be the following after we cancel some of these terms. It's going to be the following. Now, this is kind of maybe hard to interpret, but let's take a pause here and see, you know, what if we were just wanted the univariate case? Could we finish the proof now? Well, like that's saying k is equal to 1. Well, what would we have in the sort of like, let me sort of put a dot bubble, supposing we want to stop now, if k equals 1, in case the entire proof gets a bit too technical. Well, what do we have here? We have, you know, 1 over 2 sigma squared times 2, and just say x times v plus v squared. This is our privacy loss random variable. And let's take a look at this. Recall that the only part of this that's actually random is this x here. X is distributed as Gaussian, or x is distributed as n 0 sigma squared. Now what we have here is a random variable which has, say, what is the mean of it? Well, it's going to be, it's going to have mean overall v squared over 2 sigma squared, because this is sort of an additive term, just kind of using properties of Gaussians. So this is going to be n with, like, let me write it like this. The mean is equal to v squared over 2 sigma squared. Recall that's exactly what we wanted. Here we had, the sort of difference squared divided by 2 sigma squared. That's exactly what we wanted. And we'll have that the variance is going to be equal to, how do we compute this? It's going to be, recall that when you put it, when you multiply a Gaussian by some constants, they show up in the squared in the variance. So the variance is going to be equal to, v over like 2v divided by 2 sigma squared squared times this sigma squared that we already have here, times sigma squared. So this is equal to v squared over sigma squared. And that's also exactly what we wanted, right? This matches up perfectly with the variance that we were targeting. So if you find it too tough to keep going with the notation we're going to introduce now, then like note that it works out for the one-dimensional case. But let's return to the higher dimensional case and see how this proof ends. It's actually not too much harder. So what we're going to do here is like, okay, let's see how we looked at the mean here. It's going to be the additive terms. Well, let's look again at the additive terms here. Like this is going to be the only random variable. But instead, if we look at the rest of this, this will have mean equal to summation of vj squared divided by 2 sigma squared. And this is equal to the L2 norm of v squared for 2 sigma squared. So remember, this is exactly what we were going for, right? This is the mean that we were targeting. We have to do a little bit more work for the variance, but not too much more work. In particular, we want to understand, what this distribution here is. Well, 1 over 2. Well, let's ignore the additive term now and just focus on the rest of it, which is going to be 1 over 2 sigma squared times summation 2xj bj. Well, first thing we're going to do is we're going to use our definition of, we're going to use the fact that we mentioned before, where we can sort of sum Gaussians to make a new Gaussian. So this is going to be like equal in distribution to 1 over 2 times sigma squared. A single Gaussian. Okay, let's actually cancel this a little bit. Let's cancel this out, this 2 here and this 2 here. And now what we have is, 1 over sigma squared. And we're going to sum up these to create something which is like the following. So we have, this is going to be times y, where y is distributed as n0 sigma squared times the L2 norm of v in L2 squared. And where does this come from? Again, it's just by saying that, each individual component, which is, let me do this actually with step by step. So this can be written as the following. This is 1 over sigma squared times summation of x. Let's write this as another new variable, zj, where zj is equal to, is distributed as n0 sigma squared times vj squared. This is simply just using the property that I mentioned, where rescaling a Gaussian will bring any constant multiplying factor into the variance as a square. And now all you have to do is note the fact that if you add these variances up, then it'll factorize nicely and just give you a single Gaussian, which has variance equal to sigma squared times the L2 norm of v squared. And if you now just draw in this last sigma squared into this, then this will give you something which is distributed as n0 L2 norm of v into squared divided by sigma squared. And this is exactly what we wanted. it got a bit messy in the end here, but like let's take a look here. Let me highlight the important parts in say blue. So we got a distribution, we showed that this random variable has mean equal to this L2 norm of v squared divided by 2 sigma squared, and a variance equal to essentially the same thing up to a factor of 2. And this is exactly what we were trying to do in the first place. That was the claim in the lemma. So therefore, we proved that it has the appropriate distribution, and we are done. Okay, so that was a lot of work. This was probably the more technical part of the proof, but let's see what we actually learned here. What we learned now is that the privacy loss random variable is some Gaussian distribution. And all we want to say is that the privacy loss random variable is bounded by epsilon with probability 1 minus delta. So all we have to do is basically use a Gaussian tail bound to show that this indeed holds if we set sigma squared right. Okay, so what are we saying now? So the privacy loss random variable is the following. So let's write it in the following kind of weird way. So this is what we're going for. We're going to say that the privacy loss L on X prime is equal to the following. We're going to write it as f on x minus f on x prime So we're going to write it as the following, where we have this being n0, 1. So z is a standard normal Gaussian. I just sort of factored it out using kind of the opposite of the fact that we mentioned above. You know, pulling, you can convince yourself if you pulled this multiplying factor into the variance, and then let this be the mean, then you would have the true privacy loss random variable, which we proved just a little bit before. But I've written it in this form for convenience. So what we want to say is the event, our goal is to prove epsilon delta differential privacy, which shows that this will be bounded by epsilon with probability 1 minus delta. So what happens when this is not bounded by delta? We want to essentially find out the probability that this whole thing here is greater than or equal to epsilon, the whole thing here. We want to show that that's less than or equal to delta is sort of our final goal. So let's rewrite this a bit, just because, you know, this is a kind of crazy random variable here, but let's write it in terms of just z, because z is a nice random variable. It's a very, very easy to understand. It's just a rescaling argument. So really what we're trying to say is that if we really want the absolute value here, the absolute value of this. So another way, if you just sort of move things to the appropriate places, then this will be saying the probability that z is greater than or equal to epsilon sigma divided by L2 norm of minus divided by 2 sigma. Yeah, just, oh, sorry, there's no square here. And yeah, this is just a rearrangement. How do we do this? We just basically move this term over to the right-hand side here, and then rescaled by sigma divided by the L2 norm of fx minus fx prime. So convince yourself that this is just a transformation of the previous thing. And let's set, what if we set, like we said, we're going to set sigma to be equal to the L2 sensitivity times t divided by epsilon. If we plug this in here, recall that we bounded the L2, this will be upper bounded by the L2 sensitivity. So it actually simplifies quite a bit. So t is going to be some parameter we're going to choose shortly, but if we just leave it being a free variable here, so this can just be upper bounded by the following, by performing the substitution. T minus epsilon over 2t. And this again is just substituted in, and you'll see that's what you get. The only reason this is an upper bound versus an equality is because we use the fact that this is less than or equal to the L2 sensitivity. All right, so now this is a fairly nice quantity here. Like this is just really looking at a Gaussian tail bound for the most common Gaussian that we know. I'm going to cheat a little bit and make this a little bit simpler just for the sake of presentation. In particular, you'll get qualitatively the same answer, but if you want to really care about the constants, which are important in differential privacy, you should be a bit more careful with this, and in particular see the proof in Dwork-Roth. But this is approximately equal to, this epsilon over 2t is going to be pretty small. So we're just going to say probability that z, the absolute value of z, is greater than or equal to t. Okay, now let's take stock. What we're trying to do is, again, say that this is bounded above by delta. And what we need to do is find a t which allows this to be bounded above by delta. So we'll do this as follows. Like there's a very common standard tail bound, which is very useful. So this is, I won't prove this for you, but this is a common one, and I'll point you to some references maybe. The probability that a Gaussian random variable, standard Gaussian, is greater than some value v is less than or equal to exp of minus v squared divided by 2. This is like a useful fact. Now, by trying to apply this here, all we have to do is sub in the value, so with this in mind, if we substitute in t equals, say, square root 2 log 2 over delta, this implies that probability that absolute value of z being greater than or equal to t is going to be less than or equal to delta, which is exactly what we wanted. So yeah, all we really did in the second part of this proof is take the fact that the privacy loss random variable is a Gaussian and massaged it into a form which was very familiar to us, the sort of standard normal Gaussian. We plugged in, what we know is going to be the right answer. Maybe we cheated a bit, but we sort of plugged in the right answer and then showed that this t factor here, which is a multiplicative thing here, has to be roughly square root log 1 over delta. This is not surprising if you're very good with probability, in the sense that you'll know that the tail of a Gaussian decays as square root log 1 over delta. You have to go square root log 1 over delta in order to be isolating only delta probability mass in the tail. So this is kind of the natural, I claim this t is kind of natural. So yeah, that's the entire proof. We showed that sigma is equal to, the L2 sensitivity over epsilon times square root log 1 over delta, implies, epsilon delta dp. Maybe with some constant in front here. But yeah, that was a kind of tricky proof, but we made it to the end of it. So yeah, I think it's kind of nice, and it's a kind of convenient fact that in this case, the privacy loss random variable is Gaussian. In general, that's not the case. For example, when we saw the Laplace mechanism, the privacy loss random variable there wasn't a Laplace distribution. It was kind of a weird distribution, but yeah, here it's kind of magical and comes out nicely. Okay, so to conclude this lecture, we'll relax a little bit for the last few minutes of this class and take a step sort of more high level. Let's just talk about these properties of approximate dp. Not talking about the Gaussian mechanism anymore, just properties of approximate differential privacy. We went through all of these properties in the previous lecture, or maybe 2 lectures ago when we were talking about pure dp, but do they still hold under approximate dp? So let's talk about them one by one. The first one is a very useful one known as post-processing, saying that essentially if you do any algorithm to something which is differentially private, it stays differentially private. Before we had, something that's pure epsilon dp will be epsilon dp after. Well, fortunately, it's essentially the same thing here. If it's epsilon delta dp before, then it'll be epsilon delta dp after. So nothing is lost there. Post-processing is very convenient. No worse. The next is group privacy. Recall that group privacy focuses on databases which are not one away from each other, not neighboring data sets, neighboring databases, but they differ in, say, this time, k positions rather than just one position. In this case, what happens to the sort of differential privacy guarantee? Well, this one isn't quite as nice as before. In particular, what we saw before is if you have this epsilon dp, then you'll have this x to the k times epsilon, which stays now. So kind of, it sort of chains nicely, and you get this factor of k, which is kind of natural. On the other hand, the delta does not behave any nicer in the sense that, or it behaves quite a bit worse, in fact. In particular, this is the type of delta that you get in the end, in terms of like the additive probability difference, where you have, it's not just multiplied. The nice thing we would like is something like k times delta. That seems like the natural thing. But in fact, you pick up a lot of these e to the epsilons as well. So essentially you have k times e to the k times epsilon times delta. So this can be pretty bad, especially if k is getting larger and larger, because it grows exponentially in k. So not as nicely as we would have liked, but that's life. And finally, the last property we'll mention is basic composition. Recall that we said last time, if you have a sequence of algorithms where they're all epsilon differentially private, then the result will be k times epsilon differentially private. Well, now we say if they're epsilon I delta I differentially private, then the overall output of outputting all k things which are done on the same sensitive database, the overall thing will just add up the epsilons and add up the deltas. Sorry, there's a typo here. This should be epsilon I delta I. So yeah, you do a bunch of, this is kind of a very important thing for practical data analysis. It says if you do many analyses on the same data set, then you can add up the privacy parameters for each of them, and that'll give you an overall privacy guarantee. Very handy. Now, the claim is that there's something better, which we'll get to in the next lecture. I think I promised that last lecture that we'd get to this lecture, but there's more stuff. So let's suppose they're all equal to each other. They're all, epsilon I equals epsilon, delta I equals delta. Then this would overall give you k epsilon, k delta dp. Now, the claim is that there's a more advanced composition, which will give you something like, let me just try writing something which will look a bit arcane perhaps to you. Something like 8a log 1 over delta prime delta plus delta prime. So what does this say? This is kind of weirder. So the deltas still add up. You have, if they're all the same, then you have k times delta here. But what you can do is add in another slack delta prime, which goes also into the epsilon guarantee. But then it multiplies square root of k. Like this is kind of a mess. But roughly what you can think of this as being is like something like, very approximately, I'll put two approximately equal signs here. There's something like epsilon times square root k times k delta. Notice that this is a factor square root k better than before, than basic composition. So this can let you do quadratically more analyses while still keeping a strong privacy guarantee. Which is very important in practice. This type of advanced composition is crucial. So yeah, we'll get into that next lecture. But thanks for joining us today.